Hello guys, welcome back to my channel Gamma Digamma. So in this video, as I promised, I'm going to talk about differential equations, basic strategies to solve them. Because after this is sort of a filler, if you want to think of it that way. It's sort of a filler until I sort of have time to write the material for waves, and then waves to Fourier series transform, then Laplace, and then we can sort of bring it back together for differential equations, because there's also a Laplace transform method and Fourier transform method which precede Green's functions. So yep, I think that's a conventional, if not the most well-trodden path that we're gonna have. So let's get started. First category of differential equations, and I'm not going to spend much time on this, is a variable separable. So if you have some differential equation, and these are usually like first order, okay, so if you have some differential equation like this, if you can convert this into a form that's some function f of y d by equals some other function g of x dx, if you can separate the variables x and y, then you can integrate both sides and basically solve and get a relation for y and x. And the simplest differential equation you can solve with this is something that looks like this. So this is clearly variable separable, so you can just have dy over y equals dx over x, and then integrate both sides. So you get a natural log of absolute value y equals natural log absolute value of x plus constant of integration. This becomes natural log absolute value y over x equals a constant. So yep, that is pretty much it for variable separable. You can, of course, you can do lots of like questions beyond this, but I don't think there's much point doing it, because it's pretty simple, you can do it anyways. So the next method is the integrating factor method. So if you have again a first order like this, then what you can do is you can multiply both sides by this factor, which we'll call the integrating factor, e raised to the integral of this function p of x dx dy over dx plus p of x y of x equals, you multiply on both sides, so you have again the same guy, and then you notice that this thing, integrating factor times this derivative plus p of x times integrating factor times y of x, this, and you can like do this on a piece of paper if you want, is just product rule for the integrating factor times y of x. You can check this out, you do the chain rule to get this. And then again, if this is we have a derivative here, so we can just take the antiderivative on both sides to get y of x times the integrating factor equals the antiderivative of this thing over here dx plus the constant of integration, because you're doing the antiderivative here. And now again, I just want to make clear the integrating factor, we call it IF, is just e raised to integral of p of x dx. Don't really put a constant of integration up front here, because you can think of this capital C as like an accumulation of all these other constants of integration, plus it makes it a little hard. So just don't like put a constant of integration for the integrating factor. Now I can do an example of this. This is a pretty neat technique. Okay, so An example of this, as I promised, is 1 plus x squared dy over dx minus 2xy 1 plus x squared inverse tangent of x. So, well, remember in the original formulation dy over dx had coefficient 1 with it, so just divide by 1 plus x squared. So we have 2xy over 1 plus x squared equals inverse tangent of x. Now, the form of our differential equation, we had a y and then some function multiplied with the y. So as long as you can like pull this, if you can like separate a single y that's alone, then you can use a integrating factor method. And now integrating factor you can find out is e to the this guy, which is because this was p of x dx. This is not that bad to integrate. Negative natural log of 1 plus x squared. This just becomes e to the natural log of 1 over 1 plus x squared. Suck in the negative and make it a power for the argument inside. 1 over 1 plus x squared. That's the integrating factor. The solution is y times the integrating factor equals this function, integral of this function with the integrating factor. So that's inverse tangent of x over 1 plus x squared plus constant of integration to account for all those constants. So you have this, and this you can do a u substitution, but you can, I'm experienced, so I'm just writing the answer directly. It's inverse tangent of x squared over 2 plus c. So you can like multiply both sides by 1 plus x squared to get 1 plus x squared inverse tangent of x whole thing squared over 2 plus c times 1 plus x squared. And that's your general solution for y of x. For this differential equation, you can plug it in, check, it should be right. Okay, moving on. The next method of importance is a method of exact differential. Again, it is for order 1. So you have differential equation of like this form. These guys are functions of x and y. If you can write this in this way, equals 0, and then if you can find a phi such that partial of phi with respect to x, phi is a function of x and y, that's why I'm doing a partial derivative here, equals r of xy, and partial of phi with respect to y equals s of xy, then you can write this as, so you can write r as partial phi partial x dx plus partial phi partial y dy equals 0. And this is just, you can like use, you can see like the reverse chain rule or something for multivariable calculus. That's just an exact differential, phi equals 0. So this means phi is just some constant which you can find given some boundary conditions, and then since whatever phi was, you can like isolate y and x and then sort of solve it, or at least you have a relation between them. So one way or the other we have like come closer to what we had before. Now this finding such a phi is only possible when, well, let's see, we have d phi over dx equals r of x. What if we differentiate with respect to y on both sides? So we have partial with respect to y, partial with respect to x of phi, and this is partial with respect to y r of xy. And what if we differentiate with respect to x on this side for the x, for the s? And it might become clear in a minute why I'm doing this, because notice this is just, it's a mixed partial derivative of second order. This should be partial y partial x, my bad. And then we know by Clairaut's theorem that if like phi is like a well-behaved function, then these guys are equal, which means we want this equal to that. And since these are provided by the differential equation, we can just check by looking at a differential equation which is of this form whether this condition is satisfied, because if this is satisfied we can use this method, because then we can find such a phi, otherwise we can't. And well, isn't this weird? Doesn't this look a little weird? Well, if you look at this, what is this? This is just some vector dotted with the the position vector, because if you let this become r of xy, s of xy, then this is just a dot product between the displacement vector and this vector x. So what are we trying to find here? If you sort of take the integral on both sides along some arbitrary curve at 0, right? But then I hope you remember my video on Stokes' theorem. We can use that and change this like line integral into integral of the curl on along the like the inside the surface area that's enclosed by this contour. Even that's 0. But since both of these guys were arbitrary, which means this guy has to be 0, which means this is conservative. And what does conservative mean? Well, you can try to take the curl of this guy and set that equal to 0, and you get precisely this condition. So you see how Clairaut's theorem is tied to like Stokes' theorem, which is also tied to this method of exact differentials. This is just reversing this. You can think of this as like reversing the gradient or something like that, using line integrals. It's just a version of fundamental theorem of calculus in higher dimensions. So you see how everything is sort of connects, everything makes sense. Let's see this in motion now. Let me do an example. Okay, we have dy over dx equals negative 3x squared plus 2y squared divided by 4xy with the boundary condition y of 1 equals 1. You can call it an initial condition. Boundary condition is a more general terminology for PDEs. So we have 4xy dy plus 3x squared plus 2y squared dx equals 0. Now we want to find a phi such that, you know, we can like construct the exact differential out of this. So which means we can try integrating this guy for xy with respect to y. So x is a constant, 4x y squared over 2, which is like 2x y squared. Since this was integration with respect to y, we'll have some function of x which we don't know. So this is phi could be something like this. So this is our first guess. The second guess might take us a little closer, and we can combine both the guesses, integrating this guy with respect to x. So 3x squared plus 2y squared dx, and we get x cubed plus 2y squared x and some function of y that we don't know because it was integrating with respect to x. So combining both our guesses for phi, we can set g of y to 0 and f of x to x cubed so that everything is satisfied. Take the simplest case for g of y, don't like complicate things. You can think of this as gauge fixing. This will be a important concept soon when I do the Wronskian, or when I talk of like some Coulomb's law in physics. So we have x cubed plus 2x y squared as our phi. And you can check this satisfies our differential equation. To convert it into an exact differential form, because now we can write the entire equation like this, and then by the chain rule I have this, which means phi is some constant, which means phi, which was x cubed plus 2x y squared, is some constant, and we can solve for the constant. We have y of 1 is 1, so when x is 1, so this constant is 1 plus 2, which is 3. X cubed plus 2x y squared equals 3. You can solve for y squared. 3 minus x cubed over 2x, which is under a square root. And I believe you'll have to choose like the positive branch, because there's a plus or minus, but you can see the boundary condition again. If x is 1, to get y1, this should be a positive. So instead of like plus or minus, just like take a positive out of them. So this is your solution for y of x. So this satisfies the equation. You can check it. Okay, the next important method, and people don't talk about this much, is the method of quadrature. So for this you have a second order differential equation. Something like this. What you do is you multiply by d phi over dx on both sides. Okay, I mean, we didn't do much, it's just multiplication. But looking at this, you can write this as the derivative of d phi over dx, like the whole thing squared. If you take the derivative, you have like 2 times d phi over dx times the derivative of d phi over dx, which is second derivative. Since we have like this extra factor of 2 of the power rule, we can divide by 2, so we just get this same expression again. But only by doing that can we maintain equality on both sides. So multiply by 2 here. And you can integrate both sides. So we can like integrate with respect to x. So we have d over dx. This entire quantity is squared, and we're integrating it. Same thing here. Now notice that like the antiderivative of this derivative is just this guy, fundamental theorem of calculus. And this guy, you can think of like dx, this dx, and like this dx sort of like cancelling out. This is a physicist way of thinking, but kind of helps. So you have this, okay, and then just to like find the d phi over dx, you have to take a square root on both sides. And then sort of this becomes a variable separable problem. This is algebra. It's not much interesting. And you get plus some constant. Now this constant is important because like these integrations can get really horrible and bad. Like if these like conditions, initial conditions, and we need to because it's a second order differential equation. If these like conditions don't play well together, if like these like if bad variables, bad numbers don't cancel, this like answer is just gonna be like an unsolved integral which is like non-elementary. I mean that is still an acceptable solution because we still solve it, or we come closer to solving it, but it can like be really hard to solve if like using elementary methods. If so, I'm assuming after all this annihilation we get some g of phi equals x. Since we wanted to solve for phi of x, we'll just have to invert it. So that's the method of quadrature. Call it a quadrature because we're looking at sort of the square, and that's the term that remains. And again, note that we have a plus and minus here. We'll have to select a branch depending on the initial conditions. Again, the initial conditions are so important for this, and also that you can't have a first derivative term here. Like it just ruins everything. You can't use this method anymore, and you need a function of phi here. Can't have a function of x. So yeah, okay. So let me do like one example, because examples are really important for us. So we have a negative cosine of y, sine of y with the differential with the initial conditions. Y of 0 is 0. dy over dx at x equals 0 is, well, not 0 but 1. So I'm just gonna like skip steps. We have half derivative of dy over dx quantity squared. So I'm taking like the 2 on that side. Negative 2 cosine of y, sine of y, dy, because this is after integrating with respect to x. And then now integrate, and now when we integrate we need to like consider these, because there's so many integrations, it can simplify stuff later. It's good to like not have some lingering constants. So we can integrate from like when x equals 0, the value of this when x equals 0, and the value of this, let's say squared because we have a square there. When x is like x, just the variable x. We need to still like keep variables. We can't really get rid of them because we want to solve for y in terms of x, which are variables themselves. So we can do a similar thing here. Integrate from like when value of y when x equals 0, and value of y when x is x, the variable. Okay, now I can do like a quick u sub on that side. I'm not showing the steps. And then evaluate y at 0, y at x. And then this just becomes, well, dy over dx quantity squared at x minus the quantity squared when x equals 0. So when x equals 0 it's 1, so the 1 squared is 1. So you just have this minus 1 equals, well, cosine squared of y minus cosine squared of, well, y of at 0 is 0, so cosine squared of 0 is 1. See, now these guys cancel. This is important because if these didn't, this would have been a really bad integral. Now dy over dx is square root plus or minus cosine squared y, which means this is either plus or minus cosine of y. We can now check with the boundary conditions which branch to take. So if you take x equals 0, dy over dx is going to be 1. And y of 0 is, well, 0, so cosine 0 is 1, which means we need to choose positive just to satisfy this. See, these steps are really important. People forget them and people mess up big time. So we have dy over dx is the secant of y. Sorry, I'm just making mistakes. Cosine of y. This is a variable separable now. And again, when we integrate, we have these conditions, so just use them. Y of 0 to y of x, y from 0 to x. So they should match. If y is going from 0, x is 0 here, x should be 0 here. I mean, this is y of 0 is like y when x equals 0. So just understand, everything should match. It should be consistent on both sides. This is natural log, secant of y dy integrated, right? So secant of y plus tan y, if I'm not wrong, if I remember my antiderivatives right, and then x and 0. This is just bad notation, by the way. I should probably have a prime. So this is natural log of secant of y plus tangent of y minus, well, secant of 0 is 1, tangent of 0 is 0, so natural log of 1, which is 0, and we have x here, x minus 0. So x is natural log of secant of y plus tangent of y, so we have e raised to x is secant of y plus tangent of y. You can get rid of the absolute value because an exponential is always positive. I mean, is there like a way to simplify this? Well, we can find a way, because look at this way. 1 plus sine of y divided by cosine of y, which we can express as cos of y over 2 plus sine of y over 2, but like the whole thing squared. You can check this, you can use identities and check. And then this guy, cos squared y by 2 minus sine squared y by 2. So we can cancel some things out. This will just, we can use the difference of squares identity. So one factor of that cancels with like one of these. So we have cosine y over 2 plus sine of y over, because in the denominator I'm using a squared minus b squared equals a plus b times a minus b, right? So the a plus b, so cos of y over 2 plus sine of y over 2 cancels with one of these guys because it's a square, so there's two of those. While we just have the negative, which does not cancel with anything in the denominator. I hope you see this. You can pause the video and like do it on a piece of paper. I'm not wasting too much time. Now divided by cos on both sides, we have 1 plus tangent, 1 minus tangent, and you can use an identity. This is tangent of pi over 4 plus y over 2. That's e to the x. So you can do an inverse tangent on both sides. Negative pi over 4 here and y over 2. So multiply by 2. 2 inverse tangent of to the x minus pi over 2. So yep, we have solved for y in terms of x. Again, be careful of like the range of the inverse tangent. But yeah, that's pretty much it. That's method of quadrature for you guys. So I think that's it for this video. Please like, share, and subscribe to my channel, guys. Recommend me to your friends. I'm almost at 1,000 subscribers. I'm like what, 24, 23 subscribers away. So please like spread. This is the last lap so that I can celebrate There's, you don't get many occasions to celebrate when you're in college, so at least give me that occasion. So, yep. Thanks for watching and peace out.